Hi, welcome. This is functional analysis, fourth and concluding session of Hahn-Banach Theorem. I hope I will be able to finish this. Let us hope. Okay, let's get started. So in the last lecture, what we did was the following. If X is a non-linear space and Y is a vector subspace of X and F is a linear functional from Y to R, so that there exists a P, so that F of X is less than or equal to P of X for all X. Maybe I should write a Y for all Y in capital Y. Okay, what are the two properties of P? P is from X to R, so that P of X1 plus X2 is less than or equal to P of X1 plus P of X2, and P of Tx is T times P of X if T is positive. This is a very important thing. Okay, so what we proved, then there exists a G from X to R, okay, linear, so that one, when I restrict G to Y, it is F, and two, for all X in X, G of X is less than or equal to P of X, right? So this is what we proved. Okay, but what was our original problem? Original problem was if F from Y to R is continuous and linear, then I wanted to say there is a G from X to R, so that G restricted to Y is F, and 2 G is also continuous. This is linear, of course. G is continuous. In fact, we want norm of G to be norm of F possibly, but what we want is continuous extension, right? So this is our final goal. However, this is our original goal. So how do we get it? If it had gone through, I think, second session, we introduced one of the standard P is this. If F is there, F is any linear functional, okay, then we define P of X to be norm of F into norm of X. In fact, for any constant I can do that. P of X equal to C times norm of X. This will satisfy the properties which you wanted, where C is a positive thing, right? So we take this. So just to be on the safer side, to make sure that you follow, remember F from Y to R is continuous linear. Okay, therefore the operator norm of F exists, right? Remember what is the operator norm? There are various definitions, but let me just quickly look at this. Is LUB of norm of F of X, F of Y, as Y is in Y and norm of Y is less than or equal to 1. Okay, it exists, right? Then what we do, we define P from X to R now, define, so that P of X is norm of F into X, norm of X, right? This is a non-linear space, this makes sense, and this F is only a linear function, continuous linear function from Y to R, but it is bounded, therefore norm of F exists. That constant is what we are taking. All right, so if you apply our version of Hahn-Banach theorem, what does it say? There is a G from X to R, such that G restricted to Y is F, and G of X is less than or equal to P of X for all X in capital X. That means G of X is less than or equal to norm of F into norm of X. Okay, right. Now you can ask your question, okay, when I want to show it's continuous, what am I supposed to show? I am supposed to show that it is modulus of Gx is less than or equal to norm of F into norm of X. Yeah, how do I get it? Okay, think about it. I am sure all of you figured it out, right? I am sure all of you have figured it out. Okay, how to do that? But let me go through the proof just to be on safer side, those so that all of you understand this. See, what we have proved is g of x for all x in x is less than or equal to p of x. But what we want to prove is mod g of x is less than or equal to p of x for all x. But remember, mod g of x, okay, gx has to be, it's a real, remember, therefore it has to be either g of x or minus of g, minus g of x, right? This is our definition, modulus of this. Therefore, I have to prove g of minus g of x should be less than or equal to p of x. Is it true? Right? But I'm sure now all of you have understood how to do that. Now remember, g is R linear. Therefore, g of minus x is same as, sorry, minus g of x is same as g of minus x. But for all x, I know g of x is less than or equal to p of x. Therefore, it's less than or equal to p of minus x. But what is p of minus x? Remember, p of x by definition is norm f into norm x. Therefore, p of minus x is norm f into norm of minus x, which is same as norm f into norm x, which is p of x. Right? Therefore, we proved it. Yeah? Pause, review, proceed. So what have we shown? We have shown that if y is a vector space, these are R non-linear space, and if from y to R continuous plus linear, then there exists a g from x to R linear, and such that g restricted to y is f and norm of g equal to norm of f. Now does it follow? So this remains to be shown. Right? But that's very easy, because let's recall what is norm of f. Norm of f by definition is LUB of modulus f of y as y varies over b of y. What is b of y? For the time being, let me assume b of y is the closed unit ball in y with respect to the induced norm. Right? And what is norm of g? That is by definition again LUB of modulus g of x as x varies over b of x. What is b of x? Clear, right? Right. Now notice that b of y is a subset of b of x. Right? Therefore, let's look at norm of g definition here. That is LUB. Therefore, mod g of x we know is less than or equal to norm p into norm x for all x in bx also. Right? This is by construction of g. Right? But norm x is less than or equal to 1, therefore norm of p. You understand this? Therefore, what I have concluded is norm of g is less than or equal to this. Okay, each one of them is less than or equal to norm p. Therefore, norm of g will be less than or equal to norm p. Right? Each one of these numbers is less than or equal to norm p. Therefore, their LEB will also be less than or equal to norm p. Is that clear? But these numbers, okay, this is a subset. What is the subset? Modulus f of y, y is in b of y, is a subset of modulus g of x, x in b of x. Because if y belongs to b of y, then b of y is contained in b of x, and g of y is nothing other than f of y, because g is an extension of f. Therefore, this set of real numbers is a subset. Okay, but LUB of this subset is already norm p, and this LUB of this set is less than or equal to p. Right? Now recall, if A and B are subsets of R, then LUB of A is less than or equal to LUB of B. Right? Therefore, this LUB, namely norm P, should be less than or equal to this LUB, which will be less than or equal to norm P, therefore equality holds. Okay, pause, review, proceed. Okay, right. Now we want to prove the complex version. What does that mean? Now X is a non-linear space over C. Y is a complex vector space, and F from Y to C is continuous plus linear. Then we want to prove there exists G from X to C linear and norm of G equal to norm of F. In particular, G becomes continuous automatically, and G must be an extension of F. Okay, this is what we want to prove. Please understand, spend some time. This is very easy, there is nothing, right? Very surprising thing is it took 11 years to prove this. My guess is that nobody was looking for complex version. They were all working with real numbers. That was fine. Okay, they never thought about complex version because the proof is actually easy. It's something like Cauchy-Riemann equation kind of argument, which was already existing in analysis, complex analysis, etc. So when you will find textbooks will say other people were they did not know or some such thing, or it was a top proof. No, my guess is they are not actually looking for that complex version, and I'm sure they would have, if they started looking for, they immediately got it. Anyway, let us give a proof. So for that I need an algebraic preliminary. So let B be a vector space over C and F from B to C complex linear. Alright, both are vector space over C, therefore the linearity is over the ground field, namely complex numbers. Now as in complex analysis I can write f of x equal to real part of f of x and plus I times imaginary part of f of x. This is what you call as u of x plus iv of x. Right? Okay. The interesting thing is, okay, u and v are share an intimate relation, are intimately connected. This is actually Cauchy-Riemann equations for in the case of complex linear functions. Okay, right. What does it mean? Okay, let us look at. So let us look at f of ix. Okay, this by definition should be u of ix plus I times v of ix. This is our definition. But since f is complex linear, it is same as f of I times f of x. But what is I times f of x? That is u of x plus I times v of x. But that is I times ux plus minus bx. Yeah, but these two are equal, therefore this must be equal to this. Right? That means what? So this is the, just let me mark it. This is the imaginary part, should correspond to imaginary part, and the real part should converge to the real part. Right? Therefore what do we get is something very interesting, namely v of x is minus u times I v of x. Sorry, minus u times I of x. Right? And yeah, then this is the imaginary part, and v of ix should be, this is v of ix should be u of x. Okay, this is what I call Cauchy-Riemann equations. Right? Therefore I have, so if I want to find what is u, what this says is it's enough if I know u. if I know u, then I know v. Okay, knowledge of u implies knowledge of v. Yeah, so my f of x therefore happens to be u of x minus u I times u of ix, right? Ux plus I times vx, and vx is u minus of uix, therefore minus u. Is it clear? Yeah, please pause, review, proceed. Okay, so what have we shown now? To summarize, if f from b to c is linear, and if I write f as u plus iv, then my f is same as u minus ie. I should write that because now the thing is ux minus iu ix. Okay, now you can ask the next question. Is that clear? Yeah. Now the question is, suppose I have u from u to r. Remember, v is a complex vector space, therefore it's also a vector space over r. Right? Therefore, let u be a real linear functional. Right? Now let me define fx by this equation ux minus I times u of ix. I can ask whether this is C linear. Is the question clear? As usual, questions are more important. Okay, unlike many teachers, okay, I insist questions should be understood and contemplated upon. Okay, that is very easy. Remember, f is additive because u is additive. F of x1 plus x2 will be u of x1 plus x2 I times u of I of x1 plus x2, that will be u of ix1 plus ix2, because remember x lives in a complex vector space, therefore I times x1 plus x2 will be ix1 ix2, and next u is real linear, therefore it will be u of ix1 plus u of ix2, etc., etc. Okay, so this f is additive, and to check complex, it's already, we know it is a real linear also again. Okay, if I take a t real, f of tx, the t will come out. Therefore, the crucial thing to check whether it's C linear is what happens to f of ix, right? But this, according to definition, u of ix minus I times u of I of x is minus x. Yeah, therefore, is that clear? Right. Therefore, this fellow is u of ix, sorry, and this minus u is real linear, therefore minus x comes out, this is, therefore it's plus I times u of x. But that is same as take I out, therefore u of x, and take I out, this is, okay, this is I, therefore it's going to be, I can write it as I to the power 4, right? Therefore 1I comes out, okay, then it will be I squared, which will be minus 1 times u of ix, therefore it's I times fx. Okay, so f is complex linear. Okay, right? Now how do I prove the extension? I'm sure all of you now know that. Suppose f is from y to c is continuous, right? Okay, therefore write f as u plus iv, but I know this is nothing other than f of x equal to u of x minus I times u of ix, right? Therefore, to extend f, what do you think I should do? Remember, I already know the extension theorem, Hahn-Banach theorem for real valued linear functions over a real vector space, real non-linear space. So what do you think I should do now? First, notice that since f is continuous, okay, u is also continuous, because What is mod ux? Remember, if z is x plus iy is a complex number, mod x is less than or equal to mod z. Therefore, mod ux will be less than or equal to mod fx, but that will be less than or equal to norm f into norm x. Therefore, u is also continuous and it's r linear, right? Therefore, what do I know? I know that there exists and a continuous extension. Okay. Now, so I don't want to use capital U etc. because it will be very difficult for me to make sense. So let me call it continuous extension of phi from x to r, so that phi restricted to y is y over u. Yeah. Then how do I define g? For all x in capital X, you define g of x to be phi of x minus I times phi of ix. Then I know this is C linear. Okay, by algebraic preliminary. Okay, and it is continuous is also clear. Why? Because phi is continuous, x going to ix is continuous, followed by phi is continuous, followed by minus I is continuous. Therefore, this is continuous. But what I want to know is whether norm g equal to norm f. Okay, continuous extension is already done. Now what we want to do is whether it preserves the same norm. Extension also has the same norm as the original linear function. Okay, right. This is again a trick which you learn in integration. Okay, okay. This is a trick which you learn in integration. See, if f is a complex valued function, okay, and suppose you are defined interval of f of x dx or something measure space or over interval, I don't care what it is, okay, then this also is less than or equal to interval of mod f, okay, mod of f of x into dx, whatever the domain. Okay, if you have forgotten how the proof is, you will see that's the same proof. We are going to do that. Let us do it in a minute. So let us look at g of x. G of x is phi of x minus I times phi of ix. I hope I am writing it correctly. Don't, if I do something wrong, do not be irritated, but essentially the idea is clear. Alright? Okay. Now this is a complex number, right? If it is 0, there is nothing to prove. Let's assume it's non-zero. Therefore, I can write this, okay, as mod gx into e power minus I theta for some theta. That is r e power I theta. I am writing as theta as minus theta. Is it okay? Therefore, if I multiply by e power I theta into g of x, this becomes real. Do you understand that? This is the same trick which you used here also. Okay. After this, you should go back to your integration book and then try to see this kind of argument. Okay. Do you clear? But what is e power I theta of? This is real, but since g is complex linear, therefore it is same as g of e power I theta of x, because g is complex linear. But what is g of theta x? See, for g of x for any x is phi of x into this, but remember this is already real. Therefore, this should be simply your phi of e power I theta x. There is no, this is only the real part, because imaginary part is 0. Do you understand that? Now, therefore, what is mod g of x? Mod g of x is mod e power I theta g of x, but that is equal to mod phi of e power I theta of x. Okay, but that's less than or equal to norm of phi into norm of e power I theta of x. That is equal to norm of phi into norm of x, but norm of phi is same as norm of f. Right? Okay. Therefore, what we know is norm of g is less than or equal to norm of f. Okay. Pause. Review. Proceed. As we argued in the real case, okay, we know that this is also less than or equal to norm of g, and therefore equality holds. Okay, argue as in the real case. So that's it. We have proved it. Yeah, right. So you can see I have broken. Usually come this Hahn-Banach theorem less than an hour teacher might be doing in one session, but I took almost little more than 2 hours because we wanted to understand it in depth. We started with what is algebra behind that, and for even an algebraic version we give a proof which directly uses Zahn's lemma, which prepares the general case for us. Next we looked at Hahn-Banach theorem, where we extended only one dimension extra from y plus rx, so that the analysis is taken care. We understood what it is. We took little pain and did that. Then what did we do? Then we showed how to get the real version of Hahn-Banach theorem, and today we did complex version. So it's a little more than 2 hours, but I'm sure if you go through, you'll see twice you go through, you will see Hahn-Banach theorem you can do yourself without any preparation. Okay, not many experts can do that. You can do it. Okay, we will see again.